Section 8.2 talks about area of a surface of revolution. So what happens here? The first thing I want to recall, if we have a circle with radius r, if I want to find the circumference of the circle, is defined as 2 pi r, or pi times the diameter, 2 pi r. Also, what happens here is if we are given a curve, any random curve, let's say this curve, right? And I'm going to revolve this around this line, right? When you revolve it, you're going to get the image of it. We're going to get that image, right? This. So what happened, I took this curve, that's the original curve, and what I did, I revolved this around this axis. What happened, what we got a surface, right? So we revolved the curve about this the vertical axis, as you can see in the diagram. Then this solid, the solid to the right, is obtained. So obtain this. And this solid, or this surface, has an area outside, the area of the surface. We are interested to see how to use calculus to find or calculate the area of that surface, right? The area of the whole surface. So if you want to think about it from real life point of view, it's kind of think about like you're going to go to a store to buy paint, to paint this thing that you obtained, the 3D figure. How much paint you need to be able to paint the whole solid. That's what it is. So we're trying to find the area that we need to find out, because when you go to the store, sometimes you don't know how much paint you want to buy, right? And the people at the store, they ask you, how large is this? What are you painting? Oh, I'm painting a wall. What are the dimensions of the wall? They know, like, 1 gallon can paint a wall with, 5 feet by 50 feet or something. They will know. So this is a surface. It's not like a rectangular wall. That's what makes it difficult. And that's why calculus kicks in to help us find, the area of that surface. So that's what we're trying to do. So basically, what's the area of the surface for the solid obtained? That's what we are going to find out. To do that, the simplest example we look at is if you have a vertical line and you rotate that around another vertical line, right? So if you take, how it was a curve, but a line, when you say a line or a curve, the curve can be straight line. So in math, when we say line, doesn't mean straight line. It could be curve. And the curve could be straight line. But if you want to be specific, you can say straight line. You know it's a straight. And that's what we noticed on the previous section, the first example. We said find the length of the arc or curve from x1, y1 to x2, y2, and the curve was given by mx plus b, which is a straight line, right? We found the length of that arc. So if I take the curve to be a vertical line like this, and I'm going to rotate around another line, so what's going to happen? I'm going to get an image for that one. This is the one I'm rotating about, and it's going to give me a cylinder, right? So it's going to give me a cylinder. That's the solid. It's a cylinder. So how do I find the surface area of a cylinder? Well, this is how it goes. Let's say this cylinder has radius r, height h. And the way it works, even in elementary school, when we show the students, we say we take a slice. We take a slice. Okay? So it's kind of like you slice it. Take a slice, this slice here, and what are we going to do with that slice? So that slice, I'm going to find the length of that slice. That's a circle, right? And what's the length of that circle? It is the circumference, so 2 pi r, right? That's the circumference of the circle. Now to stack all these slices on the top of each other, add them up, right? If you put like 5 trillion stacks, that will cover the whole surface of the cylinder because all of them are the same. Same slices. So you could multiply by the height, and that will give us the surface area, SA, surface area of the cylinder, right? That will give me the surface area. So back to this one, notice here the radius is the same radius no matter where I slice it at. But not all the surfaces are like that. So what happened in some surfaces, like let's say here, this was the first radius. Then this is the other radius. This is the next radius. This is, see, the radius is changing, right? The radius is changing. So we can use that formula, just that formula by itself. So that's where calculus gets started here. So in this case, let's say we are rotating about the x-axis. We're going to look at two cases, either about the x-axis or y-axis. So about the x-axis, let y equals f of x be the equation of the curve we are rotating from x equals a to x equals b. X equals a to x equals b. Then the surface area, watch how we're going to define it. The surface area, we're not going to go through the entire proof, is the integral from a to b, 2 pi times y, and we'll explain what that came from, the square root of 1 plus f prime of x square dx. And also, if it's given the other way, x equals g of y, where y goes from c to d, let's say. Again, still about the x-axis. So this is about the x-axis in both cases. Then s would be the integral c to d 2 pi x, the square root of 1 plus f prime of y squared dy. So I tell the students, if there's a dx, put a y. If there's a dy, put an x, the opposite. Now, let me list about the y-axis. How would that go? About the y-axis. So again, if y equals f of x, and we are working over a to b, then the arc length s, that would be a to b, 2 pi x, 1 plus f prime of x squared dx. So if you have, again, if you have like a curve like this, and this is the axis, it's gonna go like this. So we're rotating about the y-axis, right? This is R, which is distance x. That's a horizontal distance x. That's where the x came from. And this is the length of the curve. Length of this curve. And now if it's the other way around, x equals g of y, where y we take it from c to d, then s would be the integral c to d 2 pi y square root of 1 plus f prime of x square dy. As an example, find the surface area. Find the surface area of the surface obtained by rotating the curve of equation x equals 1 plus 2y squared. About the x-axis. Sorry, back to this one. This y should be x, right? Why? Because we're doing around the y-axis. R is x. If we go back to this. Oh wait, no. What did I do here? So, okay, just so you're able to memorize it. When we did about the x-axis, when we do about the x-axis, R is what? What is R? Y, yeah, so it's Y. So it's Y. So that's why we have that Y. That's the radius. And that's why this should be still Y. That's the radius, right? So about the x-axis, that should be y, because you're revolving about the x-axis. R is y, it's the vertical distance. When we did about the y-axis, the horizontal distance now is x. So back to the problem. Let's see how to start this. Find the surface area of the surface obtained by rotating the curve x equals 1 plus 2y squared. They give you the bounds on y about the x-axis. So how do we start with this one? The surface area S equals the integral. You know the y ranges from 1 to 2. We always have 2 pi here. Now we're doing about the x-axis. So the radius is what? Y, right? Square root of 1 plus that function, which is f of y, square its derivative, dy. Two pi y, 1 plus. Derivative of that one is what? 0 plus 4y, right? 4y squared dy. You can take the 2 pi out if you like. Keep the y here. 1 plus 16y squared. And to integrate this one should be very easy with u sub. U equals 1 plus 16y squared. Du is 32y dy. So you need 32 inside and 32 outside. Now we can do this. I usually do it on the side. I forget about the bounds for now. we do it on the side to get the pi over 16 integral square root of u du. Take that thing out, u to the 1/2 becomes u to the 3/2, 2/3. Of course, plus c if you like, but that's pi over, you can reduce by 2, 1 by 2, 8, that's 24. But u is 1 plus 16 y squared, 3/2. Now I can come back to this and say it's pi over 24, 1 plus 16 y squared to the 3/2 from 1 to 2. Substitute the 2 in for y. You get 4, y squared is 4. 4 times 16, 64, plus 1, 65. So we're going to have 65 to the 3/2 minus, substitute the 1 in, we're going to get 1 plus 16, 17 again to the 3/2. And I think that's the best we can do by hand. Find the area, again, find the area of the surface obtained by rotating the curve y equals 1 minus x squared from 0 to 1 around, let's do y-axis. Okay, let's go over this one. So first thing is the surface area is the integral from 0 to 1, 2 pi. We are revolving this about the y-axis. So the radius is an x distance. Square root of 1 plus, we're going to take the function, differentiate it, and square it, dx. Derivative of this is simply negative 2x. So s will be 0 to 1, 2 pi x, 1 plus 4x squared. And then on the side, if you like to work that on the side, just the 2 pi out, x, 1 plus 4x squared. You can do the u sub, and du is 8x dx. So we need an 8 and 8 outside. That makes it pi over 4 integral square root of u du. Pi over 4 u to the 1/2 du. U to the 3/2, 2/3. So then we finish s here. Pi over 4 times 2/3. U is 1 plus 4x squared, 3/2 from 0 to 1. From 0 to 1. And the calculation should be easy. By 2, 1 by 2, 2, pi over 6. 1 squared 1 times 4, 4 plus 1, 5. So 5 to the 3/2 minus 1 to the 3/2. Next example, the curve defined by y equals the square root of 4 minus x squared, rotated about the x-axis over the interval -1 to 1. Find the surface area of the solid obtained. So now we just have to look at this function, it looks a little bit more complicated than other functions. Maybe if you like to start with this, you can rewrite it to find its derivative first, instead of working the derivative inside the radical. So then y prime, bring the 1/2 down, subtract 1 from the exponent times the derivative of the inside by the chain rule. Then you can simplify this, the 2 cancels, negative x over the square root of 4 minus x squared. Then as the surface area is the integral from the given bounds -1 to 1, 2 pi y, because we're rotating about the x-axis, the square root of 1 plus y prime squared, the one I just found, square that, dx. Now notice I have a y, as someone mentioned earlier. How can you have y and dx? We're going to replace that y with the given function. So s would be the integral -1 to 1, take the 2 pi out. The given function was 4 minus x squared. And here we have 1 plus x squared over 4 minus x squared dx. S equals 2 pi integral -1 to 1. Here we can combine the two fractions. The 4 minus x squared cancels the x squared on the top. That will give me this dx if you combine the fractions. And then using the property of square roots, you can rewrite this, the square root on the top, which is 2 over the square root of the bottom one. And notice how they cancel each other. Okay, now we got s equals, take the 2 out, becomes 4 pi integral -1 to 1 of dx, which is very simple to integrate, just x from -1 to 1. And this would be 4 pi, 1 minus -1, which is 8 pi.